Hello, everyone. My name is Sakshi Bhargav. I'm a staff data scientist at Chegg, which is an education technology company based in the Silicon Valley. Today, I'm going to talk in detail about one of our in production project, content graphs. This project employs multiple NLP techniques and has become the backbone of how our students discover, navigate, and consume content at Chegg. So, diving right in, we have a wide array of content created by students, experts, or educators to supplement many facets of higher education learning. Given this sea of available study material, content discovery in particular becomes difficult in the absence of a catalog. So hence, goal of this project is to present the content in a structured and organized manner, similar to a textbook or a lecture course. So we have recently expanded on the types of content available for student learning. The model in production does not cover these new types yet. So the first step was to define the organizational structure, taxonomy, that would make up the catalog. So our content and experts team did most of the heavy lifting here and hand curated an extensive hierarchical taxonomy. This encompasses hundreds of academic subjects and spans 8 hierarchical layers of specificity. It starts with subject at the top, followed by courses, and then topics. Each course can have multiple topics, and topics themselves have a depth of around 4 layers. Topics are analogous to chapters in a book if you assume course is a book itself. So that's the analogy. And lastly, like each topic at every level has a set of terms associated with it. Uh, these terms are the most granular level in the hierarchy. The diagram on the right here is an example of taxonomy tree of subject physics. So now with such varied content and this large hierarchical taxonomy, cataloging can get to a size that is prohibitively expensive to manually label. This will increase problems of information retrieval. So we need a generalizable automatic solution to associate items in a semantically meaningful way. So enter ML models. So, given the front of the flashcards in a deck or the back of the text of the same flashcards, we can infer course classification and topic information. Similarly, given a question and answer text, we can infer, again, course and topics. And lastly, with the given a book title and subtitles, we can infer close classification. So, all these information the content taxonomy and these inferred relationships are further stored in a graph database. This has resemblance to a knowledge graph where the content and taxonomy are the nodes and the inferred relationships are the edges between the two. This information is further used in various downstream use cases like recommendations, search, student posted routing questions, routing to experts, and course pages or dashboards, which might house like relevant content or the most popular content. Um, as we set out to create these document tagging models, we encountered multiple challenges. So we had highly imbalanced training data and also very limited label data. These both stem from the same problem, that we have like a huge amount of content and which is unlabeled, and we also have like a large hierarchical space. To give an idea of the extent, we have around thousands of courses, and each course has more than 100 topics. So this poses a problem that the hierarchical space is too large of a label space to work with. And then we have another problem, which is the taxonomy update. So the model and inferences should keep up with the changes in the taxonomy, such as course or topic addition, renames, deletion, or merges. Um, Lastly, we have a large amount of complex unlabeled data, And although this is practically unlimited, but it comes in various shapes and forms, and it poses some difficulty to harness it in a meaningful way. So, all the techniques or strategies that we have adopted are aimed to counter these challenges. So, now I'm going to give an overview of our content classifier pipeline. The orange boxes here are the major steps in a typical ML lifecycle, and the purple boxes beneath it are the specific methods or techniques that we applied for our project. I'll definitely cover some of this in detail over the subsequent slides, but this is just a very high level view. The first step is to collect data, both expert tagged and noisy unlabeled data. The second step is text pre-processing and preparation for model training. The third step is defining the model architecture, training of the models, and also hyperparameter tuning. Fourth is evaluating the model performance for the desired task on the metrics of our choosing. And lastly, deploying the model, so model serving, getting inferences from the models and storing it at a desired location and retrieving that information. So let's proceed to the first step of the pipeline. In the first step, we are doing data collection using annotations. So, with the help of our subject matter experts, we expanded our topic label data, especially for popular and rare categories. So, what we did was we created this annotation task and presented the experts with the text of the document. So, as you can see here on the left, and we collected tags for course, topics, and subtopics. We additionally provided labeling guidelines so that they are able to execute the task in the desired way. And also, we shared like visuals or word clouds of all the terms present within the topic so that it can give a sense to them as to what a topic is composed of and also to understand the hierarchy within the topics. This pipeline is automated end to end, and it has the capability to with the end-to-end automation, we have the capability to set up a similar task in the matter of a few minutes. So annotations definitely form a major chunk of our training data, but they are expensive and time consuming. Hence, we explored alternate solutions to artificially generate this training data using proxy labels. So the strategy we adopted is very similar to the concept is very similar to collaborative filtering. So what we do is we have an underlying assumption. So based on the study patterns of the students, what we assume is like if a student is working or studying using some materials in a limited time span, they would be mostly referring to the same courses and topics. So this is our underlying assumption. And what we do is once we have gathered all the label data, we take like the one content item which is already labeled and analyze the co-views, like basically all the other content which was viewed close to it in the same student session. So when any content are viewed close together in the same session and they fall in under the same course, we are calling them co-viewed content. And of this co-viewed content pair, one of them is labeled and the other one is unlabeled. So we rank these co-viewed pairs based on their popularity, and popularity by popularity I mean the distinct number of users who are viewing this content. And after filtering on that, we tag the unlabeled content item with the same topic as the labeled item in the content pair. So, for example, if we were focusing on deck A and deck A had topic mitosis or meiosis, then deck B, which was co-viewed with it multiple times, will get the same topic. So this definitely gave some respite to our labeling data problem, training data problem. And so now moving from data collection to model training, this is a comprehensive view of our model framework. The model, as you can see, is trained for multiple tasks here. There are a few primary tasks which we are targeting, and there are a few auxiliary tasks. So the primary task, one of them is course prediction. So given a question or answer text or a front of the card or back of the card text, predict the course classification. So this is a multi-class classifier with a cross entropy loss. Similarly, we have the another primary task, which is the topic prediction. This uses a different set of network, which is the CMEs network, and the loss used here is triplet loss. So these two are the primary tasks, and these are supported by multiple related tasks. So there is topic course pair prediction, topic term pair prediction, question answer pair prediction. Question answer can also be front of the card, back of the card pair prediction. So all these other tasks are trained using the cross entropy loss, and these all are trained together simultaneously. One thing that I would like to highlight is, as you can see, there are just two colors in the text inputs. These are all the inputs to the various tasks are text, and these are trained using different model architecture. So for the one in the gray boxes, we use a word character embedding model, and for the ones in the pink boxes, we used transformer embedding models. Why those and what's the importance will definitely go in details in the subsequent slides. But now I would like to focus on the topic prediction using triplet CMEs networks. So what is a CMEs network? Why and when do we use it? Traditionally, a neural network learns to predict over fixed multiple classes. This poses a problem when we need to predict for a rare topic or for which we did not have any training data at all. This, as you can imagine, is a common scenario in our case because we have a very large hierarchical taxonomy and there are just so many topic labels for which we have no training data. So, in such a case, usually when we want to predict for the new class, what we are doing is we are adding a new class at the time of inference to the label space. So in such cases, ideally, we would collect some training data first and then add it to our model for retraining the whole architecture. So this is how we will be able to incorporate our new classes. But this data is usually not available, as we have seen, like we have to rely on annotations and proxy labels, etc. So to address this issue, we use a different class of neural networks called the CMEs networks. These consist of identical subnetworks, usually with the same architecture and weights. Triplet CMEs networks, in particular, have three inputs: the anchor, positive, and negative class. So the anchor and positive usually belong to the same class, and negative is a different class. The idea here is to learn distributed embeddings representation of data points in a way that contextually similar points are projected close by to each other in the latent space and in the vector space, and the negative and the anchor are just far off from each other. Uh, this happens after the model has completed its training. So when we want to apply it to our use case, we see that the anchor is the context, the text of the content, which can be question answer or the flashcards, etc. So that becomes the anchor, and the positive label is the ground truth topic, and the negative label is any topic sampled from a list of topics. With this, the model is trained using a loss called triplet loss. The idea is the same here. It's just to push the encoding of the content and the positive topic close to each other in the vector space, whereas far from the negative topic encoding. and this is usually separated by a margin, which we can find it analogous to like how the loss operates in case of SVM. This similarity based learning and the distance based loss function enables us to classify new classes of data without training. So there are multiple options to define and sample these triplet inputs. First is, how do you even define, like how do you find these triplets? So A option is you can look at the entire training data and then do negative sampling to find these triplets. But in general, this requires a large amount of data and you have to process all of it at the same time. Then the other option is, while you are training, you can negative sample from the training examples present within your batch. So this form of sampling or negative mining or mining of the triplets is called online mining, and it generally leads to faster and efficient training with lesser data. Besides how to find these triplets, there are also different types of triplets. There is easy triplets and there is hard triplet. So if you are sampling the negative topic from two very different courses, for example, let's say physics or biology, then naturally they appear very far off from each other in the semantic space. So given that distance, the network will not learn much if we try to train on these easy triplets. So what is needed is we need to sample probably within the same course. Like if we sample within the same course, the topics would be really close to each other in the semantic space. And that's why the network will have to just work much harder to learn and push the differences by a margin. So these are called hard triplets, and they generally lead to better generalization and reduce the risk of overfitting. So for our use case, we chose online mining and hard triplets for the reasons I just explained. So we saw that our model that was trained was a multitask model, which was training multiple tasks at the same time. This technique is intuitively called multitask learning. And there are mainly two categories of tasks. One is the primary task, which the model is actually targeting. And then there are auxiliary tasks whose sole objective is to improve performance of one or several primary tasks. So why do we need this? Imagine learning to ride a bike or learning any new task. We often apply the knowledge that we have pre-acquired from learning related tasks. Sometimes also what we do is, if you want to learn a complex task, we would probably learn the simpler tasks first. So similarly in machine learning, the knowledge gained in one task can benefit other tasks, which is also the concept of transfer learning. One big advantage here is that the model learns better and faster in a limited data scenario, which is definitely contrast to the single task learning models, where we are training with the objective to learn only a single task and it requires a huge amount of data. Training a network on the variety of tasks also leads to inductive bias. We can then see improvements in generalization over training each task separately, because the multitask network in general penalizes overfitting for a single task. So this is the whys. Now moving over to how we do it. So we performed uniform sampling to collect almost the same number of data points for each of the tasks. Then what we do is we learn a common space representation by completely sharing weights and parameters between tasks for a few layers. This shared feature space is used to model the different tasks. Along with it, we can also have optionally a few task-specific layers. These task-specific layers are trained independently for each task, or they are learned independently for each task. The losses that are present for individual tasks are weighed differently depending on the importance of the task. So for the multitask model, the training is while it's training, we train for the weighted sum of the task specific clauses. There are a few challenges in multitask learning as well. We need to assess how closely related or far off the tasks are. So, in our use case, we took care of this by choosing the auxiliary task to have the same input or the combination of inputs that went into the primary tasks. This also eliminated like a little bit of the other problem, which is the competing objectives between the different tasks, which is very much a possibility. When the objectives are competing, this generally leads to poor performance, and definitely we need to pay attention when defining our architecture or choosing the tasks. Lastly, as you can imagine, like we did uniform sampling, so this is a requirement for multitask learning. And what so happens is usually the size of the data set for each task is bottlenecked by the smallest data set present for a task. So what we don't want is we want to definitely give a free flow for our primary task and don't want to hamper it by the limit in the data available for any other tasks. So for our use case, we specifically chose for auxiliary tasks unlabeled data or data with implicit labels so that there are no size restrictions. So that is all about multitask learning. Now, as I have mentioned, for the different text inputs, we use two kinds of architectures. First is the word and character embedding model. This, as the name says, intakes both word and character level text input. The advantage of encoding on both and word and character level is that the model is able to overcome out of vocabulary cases, which is kind of a requirement for us because, like I said, we want to infer or predict for new classes too. So be able to so that the model is able to learn not just the words but also the characters within the topic labels or any other term labels, course labels, etc. The character encoding is very useful. So we have used CNN here. CNN layer is used with, and it has like local connections, meaning you add a filter on the top of the inputs and we connect them locally to extract features. The CNN and the pooling layers together are useful for classification tasks because they are great at picking local clues such as phrases that might be directly present in the category itself. So, for example, mitosis, meiosis, that might be present in your document and might be a topic itself. So, CNN does a good job in such cases. Um, in the prior versions of our network, we usually just relied on this network to encode both our labels as well as the content documents. But CNNs in general are good at fast extraction of local and positive position invariant features, which are best suited for short text. Short text like the course labels or the topic labels or the term labels. For the content documents, which are usually very long text, consists of multiple sentences, we move to a different architecture, specializing specifically in longer length, and also we intended to take care of the context, that is the neighboring words into account when we are training for the embeddings. So in a sentence, like words appear in a sequential manner, and the context of a word is dependent on its neighboring words. So there are many networks that help us to model such kind of a time sequence structure. We have RNNs, but RNNs suffer from like a vanishing gradient problem, and they have trouble remembering long sequences. LSTM, on the other hand, they are able to do a better job than RNN, but they cannot attend the data in parallel, making it slow for any practical use case. CNNs are less sequential, but they are limited by filter spans, and the complexity still goes exponentially. With transformers, these computations are executed in parallel, making them efficient and requiring less training time. They account for the context, so they are parallel, but they account for the context by baking in the order or the position information in the input sequence, which is known as the positional embedding. The transformers are able to provide us contextual embeddings where the token representation is based on the specific neighboring tokens using self-attention. It focuses on subword tokens and as opposed to the character tokens, and they are able to hold meaningful representation of many of the keywords, prefixes, suffixes, etc. So, to what the encoder essentially does, it computes attention score, which are a representation of the correlation between the words. And that's how it represents the context. So, what we see here in the transformer encoder is a multi head self attention layer. That means the same attention scores are calculated using multiple heads. Multiple heads, say, for example, if there are H heads, then the attention scores will be calculated H times. So every time these scores are calculated, we are able to attend to different parts of the sentence or the sequence at different times, and then we learn these multiple relationships between the same words. Um, our pipeline uses transformer encoder to procure the encoding of our content, which is the question, answer, flashcards. And embeddings are not just for the tasks at hand, but also we can use them for transfer learning to other downstream ML models. So from moving on from training to evaluation, the primary metric that we used here was the top 3 accuracy. The baseline model here is a single task model, say course or topic prediction, with very limited training data, mainly from expert created content. The baseline model here used the word character embedding model for both content and tags. And with addition, as you can see, with addition of all the techniques that I've mentioned so far, the performance improved. And the final model is inclusive of all the techniques that we have seen today. The deployment, coming to the deployment pipeline on the right is just a very high level view. In the end, we have like 2 endpoints, one for the course and one for the topic. These are kept separate just for efficient incoming traffic management. The endpoints are also load tested here. We use TensorFlow serving for our submodels, which provide a big boost to the inference time because they are able to just pool together the inference requests. And these batches of requests are processed concurrently by the model. It also additionally helps with model lifecycle management. Like it makes it easy to deploy new algorithms or experiments while keeping the same architecture and APIs. So what we just need to do is just essentially add submodels to your config files. And lastly, once we had deployed, both our archive and new content are tagged using the knowledge and ingested in the knowledge graph. As you can see here, the inferences are stored in the graph database. And with these ingestion, the content graphs were thus manifested. So the yellow node that you see here is represent content. Here it's the deck of flashcards. The blue nodes here are the top 5 topic inferences for that content, and the edges are named and connected as deck is described by topic. So these are the content graphs, and this is how all the techniques and the pipelines that were used for these projects. And with this, I conclude my talk. Thank you so much for your attention.